Zach, thanks for the very kind introduction, and to you and to Greg also for organising this this virtual visit, which has actually been very enjoyable. It's been very nice chatting to your colleagues and your group. So just point out a few things before I start. This is Edinburgh, is where I'm being beamed in from. Edinburgh is the capital of Scotland. It's a very beautiful country. So when we're allowed to travel again, then do put it on your itinerary. It's a fantastic scenic country, and Edinburgh itself is very scenic. This is the sort of view that you get actually just walking up from the chemistry department. You can go and have your sandwich and look down from Blackford Hill, and you see Arthur's Seat, which is an old volcanic plug, basically, from many millions of years ago. It's nice to have the countryside inside the city. You can actually see where I'm beaming in from. Actually, this is my house here, where the red arrow is. So I want to talk about polymers of intrinsic microporosity today. Really, how we are controlling free volume within polymers, within glassy polymers. And just going to start off with a bit of a philosophical slide. The sort of absence of something has always bothered philosophers. So, for example, Aristotle didn't really believe that a vacuum could exist. He felt that immediately, so if you tried to make a vacuum, there would be that things would just try to fill it. And this is effectively where the phrase that nature abhors a vacuum comes from. However, Lucretius, about 2,000 years ago, really got things quite right in the nature of things. He said that nature has two forms that make it up: the atoms and the void, where atoms are placed and travel their varied paths. And that's a pretty good description of a polymer, really. And oops, seem to have stuck. Oh. Yeah, that's not a good start. Ah, there we go, just catching up. So polymers do sort of abhor a vacuum. It's more that they actually like wrapping around each other and getting as much contact between one molecule and another. And in a sense, just to put it a sort of modern twist on things, what we're trying to do is make polymers socially distant from each other, as opposed to really just wrapping around each other. But we're fighting against polymer cohesion forces, the reason why one polymer likes to wrap around another polymer. But as I'll show you, it is possible to create voids, or really, as Zach says, to self-assemble, so voids are created, and which allow molecules to travel their varied paths through the polymer. So we're going to be talking about microporosity, and what we mean by that is the IUPAC nomenclature of microporosity. In other words, interconnected pores that are less than 2 nanometers in diameter, as opposed to perhaps engineering microporosity, which means about microns of things. So we're talking with the very smallest of pores. And when you think of microporous structures, you probably immediately think of crystalline ones, such as zeolites or moths in this day and age. But it's absolutely fine for a porous material to be amorphous. And in fact, one of the most useful of all microporous materials is activated carbon, which has this kind of structure where you have all these extended graphene sheets all packed together in a higgledy-piggledy amorphous manner. But these can have very high surface areas, very high microporosity. And actually, 20 years ago, I came up with the idea of trying to make a sort of an organic activated carbon, where instead of having graphene sheets, I'd use these large phthalocyanine macrocycles, which is something that I've been working on all through my career, is phthalocyanine chemistry. But phthalocyanins like to pack on top of each other like dinner plates, and so I had to come up with a way of forcing the phthalocyanins not to do this. And the idea was to have them joined via effectively a sort of ladder type system through the linking groups, where there'd be a spiro unit, and that spiro unit would force each phthalocyanin to be effectively orthogonal to its neighbor. And that was the idea that I had about, say, well, over 20 years ago now. Now, to get this to, I'm not sure why this is being so sticky. I have to come out of this for, I'm not sure why this is coming up on me. Try that. There we go. Okay, so in order to get this this structure, I devised this synthesis, which involved making this bis phthalonitrile, which by a metal template reaction to make the phthalocyanine would therefore create this this hopefully microporous phthalocyanine network polymer. And to do this, I chanced upon this commercially available bis catechol, which I call bis catechol A. It just so happens that this is commercially available. It's the product between the condensation reaction between acetone and catechol. So it's very easy to make, but it's also commercially available, very cheap, and also this dichlorophthaleonitrile. So react these two together by an aromatic nucleophilic substitution reaction, get this bis phthalonitrile, and use a metal to do the template reaction. And this worked very nicely. Got surface areas 500 to 800 meters squared per gram, and we could get this this network polymer, and could actually do some catalysis on this. The whole point of this was to have metals in the phthalocyanine, which would, like cobalt, that you could do some oxidation type catalyst. It's worked very well. Ew. Why is this happening? I just have to do, so I have to by forwarding the slide on here. So so the important structural unit here was this spirocenter, and if I just show you what that does from this molecular model, you can see that the spirocenter effectively introduces this 90-degree angle, this kink, and stops this structure from being planar, and that's an important parameter for this this particular network polymer. But also we use this benzodioxin type linkage, and this became very important, and I realized that this is a very efficient way of making a ladder type structure for linking things together. And so immediately we thought we could actually make a porphyrin type network polymer using our bis catechol A, as we now call it, with this commercially available tetrafluorophenol porphyrin. And you just carry out the same aromatic nucleophilic substitution reaction and make your benzodioxin linkage. And just from two commercial materials, you can get a very nice microporous porphyrin-based network, which actually has surface areas over 1,000 meters squared per gram, and you can choose the metal that you want to put in after you've formed the network. So this is all very nice. But became quite intrigued by the efficiency that you could carry out the benzodioxin formation. And there was a nice study by Jeff Eastman who showed that you could take catechol and the appropriate fluorinated aromatic compound and just carry out this double nucleophilic aromatic substitution reaction, and you get isolated yields of 99%. And that really makes you think that you might get away with a step growth polymerization, because as you know from Carruthers equation, if you don't get your reaction going in a sort of efficiency of well over sort of 95% efficiency, then you won't get a high molecular mass step growth polymerization. Now, this idea is actually quite an old one. The great Speed Marvel, one of the real pioneers of polymer chemistry, had tried to make benzodioxin type polymers back in the 60s by reacting these two monomers together. but he got an insoluble dark powder, in other words, some sort of brick dust that he couldn't really characterize very well. And looking at that structure, it's not really surprising that that was very insoluble. So we tried similar reaction, but with this bis-catechol A with a spiro unit in there, and this commercially available tetrafluorotethalonitrile. Both of these commercially available from Aldrich, and we made this polymer here. I can't do that. So both structural features are there. You have the spiro center and you have the dibenzodioxin linkage in your polymer. And this was a very efficient reaction. You could get molecular masses, or at least apparent molecular masses of over 100,000 grams per mole quite readily. And what was perhaps surprising to us initially was this polymer was soluble, highly fluorescent, but you could dissolve it easily in THF and chloroform, despite its completely sort of spiro and ladder type structure. You could precipitate it, or you can actually form nice robust films from this from these solutions. We know now that it's got a glass transition temperature of over 400 degrees centigrade, and that probably makes it one of the highest glass transition temperatures for a solution processable polymer that, or low molecular mass material, in fact. What also came as a bit of a surprise at the time, because we assumed that you needed a network structure in order to sort of maintain microporosity, was that this powdered polymer absorbed nitrogen very, very well, and particularly at low partial pressures, which indicates a sort of microporous structure. And you could calculate an apparent BT surface area of around 780 meters squared per gram from this powder. So this is a very unusual form of microporosity, and what we realized was that this microporosity comes about because of the rigid and contorted structure of this polymer, and we termed this intrinsic microporosity. So in other words, these rigid and contorted structures just can't pack efficiently in the solid state, so that leaves lots of what polymer chemists would call free volume, but there's so much free volume in there that it acts as though it's interconnected microporosity. So we able to probe this microporosity in various ways by gas adsorption and modeling that data, and you can show that you've effectively got a pore size distribution which peaks at around well, about 0.4 nanometers or so, pretty much in the range that an interesting range for gas separation, as I'll show you, in that the gas kinetic diameters are in the range 2.5 to 4 angstroms. Perhaps the best way to really visualize this is from modeling, and we collaborate with Corey Kalina's group in the University of Florida to model our structures now. And you can get this idea of what this free volume looks like. This is all the PIM1 chains, and they're just packing very inefficiently, leaving all this free volume. And this free volume is effectively interconnected and acts like a microporous material, not too dissimilar in structure from that of, say, activated carbon. What's important to realize, and this will come up again, is that the free volume that we have here is not fixed like it would be in a zeolite or a moth. We can swell it up in solvents, or we can lose it through aging, and so that it is not a fixed type of microporosity. So immediately my colleague at Manchester, Peter Budd, who had an interest in membranes, said we should try to make some membranes out of what we could now call PIM1. And you can actually see that PIM1 is solution processable, and therefore makes actually quite nice real life membranes. So this is a PIM1 about a micron thick on a macroporous support. It looks like sort of wallpaper or something like that. So you can make sort of meters from a squared of membrane just from a gram of PIM1. And this is a hollow fiber. You can see it's hollow. You actually want straight hollow fibers, but this is just a curved one just to show you what it looks like. And if you have either of these forms, then you can make a real membrane. Now, there's an awful lot that goes into membrane engineering. There's sort of all sorts of substrates that you can adapt. The way that you devise the module and how you put those modules together are all very important to the ultimate separation process. So, for example, this is like an aircraft hangar-sized building in Saudi Arabia, I believe, for natural gas separation or purification. And each one of these large cylinders is packed full of these hollow fiber sort of modules for doing separations. So it's a very large scale membrane separation. But really, ultimately, your membrane will only be as good as the separating layer that you use, and that is what we're interested in. So the sort of very thin, often micron thick layer that you have in your membrane that determines how efficient your separation will be. Now, the important thing about separation membranes is that they do have the potential to save an awful lot of energy. There's something, this is from a nice paper by Ryan Lively, and he says in this that something approaching 20, well, a massive amount of energy is consumed by molecular separations of one form or another, whether that's water purification, gas separation, just separating things like petroleum from one from another. And basically membranes, if membranes were used for all of these processes instead of, cryogenic type processes or distillation, it's possible that you could save something like 90% of all the energy used for these separations. So membranes have colossal potential for saving energy in large scale separations. So let me just show you a little bit about what we're dealing with polymer membranes. This is a little cartoon, but really you have, say, a feed mixture. Say this is natural gas processing where you want to separate out CO2 from methane, and effectively your membrane really is acting as a molecular sieve, letting the smaller molecules through and retaining the larger molecules, say the methane over CO2. And the two important parameters for your material that you're going to make the membrane out of is permeability and selectivity. So let me just show you some data for three very disparate types of polymers, including PIM1. Matrimid is effectively one of the state-of-the-art for polymers used for making industrial membranes at the moment. It's a polyimide and it's got a fractional free volume of around 10%. And we're going to quote from now on gas permeability in this unit called bara. If you look at the bottom, this is where the SI unit for permeability is, which is why we use baras, because they tend to give you nice sensible numbers. So for Matrimid, you get oxygen permeability of around 8 bara and nitrogen permeability about 1.5. So you get an oxygen-nitrogen selectivity of around 6 bara, which is adequate for oxygen-nitrogen separation. If we go to the extreme of permeability, you come up with this strange polymer called polytrimethylsilylpropyne, or PTMSP for short, and this has a very high fractional free volume, something like 30%, and massive permeability. So oxygen permeability is something like 9,000 bara for a freshly prepared PTMSP film, but oxygen-nitrogen selectivity is almost no selectivity. It's very, very unselective. So PIM1 has an oxygen permeability right in the middle, something like 400 bara, and a respectable oxygen-nitrogen selectivity of around 4. Now, these two important properties of permeability and selectivity in polymer membranes there's a distinct trade-off. In other words, you can get, as you could see from that data, You can either have very high permeability, so this would be PTMSP down here, but very low selectivity, or you can have very high selectivity over 10 for oxygen nitrogen, but that comes with very low permeability. And that's a sort of intrinsic trade-off to polymers, and I'll talk about that in just a bit more. Ultimately, what we'd like is both high permeability and high selectivity, and we'd like to get into this sort of region here if possible. Now, this trade-off has been quantified by Robeson, and he plotted all the data for various polymers onto what he calls his Robeson plots, or what we call Robeson plots. And you can see a colossal amount of work went into gathering all of this data. And then he puts these upper bounds on these diagrams, and these effectively represent the best sort of compromise between permeability and selectivity that you can get for polymers. So these Robeson plots demonstrate effectively the continuum of size distribution of free volume in solution processable polymers. So you can really only have solution processable polymers on a Robeson plot, even though people use Robeson plot for all sorts of things. But Robeson really states that they're only solution processable polymers. And the upper bounds that he draws on here really shows the state of the art for molecular sieving that you can get from a polymer. As you can see, I've plotted that polyamide matrimid here, PTMSP and PIM1, and you can see that PIM1 is a nice compromise between the two. So the Robeson upper bounds, you can have an upper bound for each of the gas pairs that's of interest. So all sorts of different important gas pairs that you might want to separate one gas from another gas. So you might want to do oxygen or nitrogen enrichment of air, for example. So that'll be O2, N2. You might want to recover hydrogen from the Born-Haber process for making ammonia, and that's an N2, a H2N2 separation. If you want to do carbon capture from a power plant, that would be separating effectively CO2 from nitrogen. Mentioned this one before. This is natural gas upgrading, so you're separating out CO2 from methane, and this would be pre-combustion carbon capture. So there's all sorts of important gas separations that you might want to do on a commercial large-scale basis. And for Robeson plots, the slope of the upper bound is actually determined by the difference in the kinetic diameter for each of these gas pairs. So for an easy separation, for example, separating hydrogen from methane, relatively easy because there's a large difference in the kinetic diameter of those two gas pairs. So you have a very sort of steep upper bound in your Robeson plot. Whereas oxygen nitrogen, there is very little difference in the kinetic diameters between oxygen and nitrogen, so you have a fairly shallow upper bound for oxygen and nitrogen. So Robeson basically says that each upper bound is the consequence of the strong size-sieving nature of the stiff chain polymers that define it. So the only things that really get onto the upper bound or define the upper bound are very stiff polymers. Now, another guru of membrane science is Benny Freeman, and he brought out this wonderful paper back in 1990 in Macromolecules, and he basically told us really how to beat the upper bound, how to get polymers that will have much better data and will be able to get above the Robeson upper bound. And he basically says that simultaneous chain stiffness and interchain separation increases can be used to systematically improve separation performance. So let's just look at those individually. This is the initial data for PIM1 plotted on the oxygen-nitrogen Robeson plot. So if we just look at interchain separation, this is increasing the free volume within the polymer. And what that really does is increase permeability. So it allows things to go through the polymer much faster, the gases to get through. But unfortunately, it also allows bigger gases to get through easier as well. So what happens is you slide down the upper bound and you get to the region where you are with with PTMSP. In other words, highly permeable, but not very useful because there's no selectivity. Much more interesting is to increase the stiffness of the chains, because what that does is reduce the thermal motions within your polymer, and so enhances the diffusivity selectivity. In other words, it allows the smaller molecules through at the expense of the larger molecules, which can't get through because the motions that it needs for one to hop from one part of free volume to another is restricted by the rigidity of the polymer. And if you can do both, then you get into a very nice area of the Robeson plot. So basically, we're dealing with solution diffusion. So permeability is related to both the diffusivity selectivity and the solubility selectivity. And we're going to be dealing mostly with diffusivity selectivity and enhancing that by our PIMs. But also, I'll touch on a little bit on selectivity, on solubility selectivity a little bit later in the talk as well. So let me just expand the interesting part of the Robeson plot. So this is above 100 baras for oxygen and nitrogen, and take you back to the bad old days before PIMs were invented, back to 1991 with the original Robeson upper bound. And he defined that upper bound using these two molecules, PTMSP, I've introduced this before, and this other polyacetylene, and basically said that the polymers that define the upper bound are effectively high TG glassy polymers, which back then were polyamides and polyacetylenes. When PIM1 came along, initially we just used effectively a solvent cast film, and we got oxygen permeability of around 370 bara and an oxygen nitrogen selectivity of 4. That placed it well above the original 1991 Robeson upper bound for oxygen nitrogen. And then Robeson took this data and effectively moved the goalposts on us by increasing the position of his upper bound. So that became the 2008 Robeson upper bound, and he said that this was now composed of ladder type rigid polymers, which is basically what PIM1. PIM1 and PIM7 was used to define most of the 2008 upper bounds. What we found out about the same time was that if you take your PIM1 film and just treat it with methanol, just soak it in methanol, is that you can actually get much higher gas permeabilities. So up to around over 2,000 bara, but you do lose quite a bit of selectivity, and so you can actually tune the sort of porosity to the permeability by this process. So in effect, you can move your pore size distribution or your free volume element size distribution by methanol treatment, which you can effectively make these free elements of free volume larger by using methanol, and you can leave the film and age it over time, and you lose your free volume, and you lose permeability, but you gain selectivity. So your pore size distribution effectively becomes smaller. So now it's quite important to realize that each polymer does not have one precise data point for permeability. I've plotted here all of the data that I've collected for PIM1. PIM1's been made hundreds of times now by lots of people, because you can buy the monomers so easily and do the chemistry, and they've reported a whole range of different permeabilities and selectivities, as you can see, a sort of data cloud here. What's interesting, if you leave the PIM for a long time, so if this is data for 4 years, then your selectivity actually goes up to something like 5, which is actually quite impressive, almost up to matrimid type of selectivity. But as you can see, there is quite a distribution of different data for the same polymer. And this is different groups using different equipment, slightly different batches of PIM1 can give slightly different results and also the thickness of the film can actually determine how fast the polymer film ages. So you get all this sort of wide variety of data just from the same polymer. So why this age data is important is because it really gives you an indication of what a real life membrane might perform like. So Ryan Lively's group went to the enormous effort of making hollow fiber membranes from PIM1. They had to make something like 10 kilograms of PIM1 in order to do this study, which is quite a feat in itself. But then they worked out how to make lovely hollow fibers. And but the thing about hollow fiber is it's only the outer surface that's actually the selective layer, and this may only be a couple of micron thick. And it's believed that this is only about 2 micron thick for these PIM1 hollow fibers. So very thin films age very quickly, and so that in a couple of weeks this had aged the same as a 100 micron thick film had in 4 years in effect. So this is the data that he got from his hollow fiber membranes. So you got nice selectivity of 5 and a reasonable permeability of around 200 bara for his hollow fibers. So during this was a lucky break. PIM1 was not really devised originally to be a membrane forming material, and we got lucky by PIM1 and we moved effectively the Robeson upper bound, and so therefore we thought, well, this is just the first of a series that we can do. We can massively increase the selectivity and the permeability by polymer design. And this actually proved much harder than I'd anticipated. So lots and lots of sort of false starts, all sorts of problems. So for example, many PIMs we made proved to be insoluble, so you can't form a film. And some of these actually we should probably come back to, because we've realized that you can use quinoline for really difficult polymers, and probably some of these may well be soluble in quinoline, but it's a horrible solvent to work with, but it actually can give you quite nice films. The other problem was that you might have get a soluble polymer, but then you just can't either get the molecular mass up enough in your synthesis, or intrinsically some even this had a very high molecular mass, but this polymer could just not form a robust film to do gas permeability measurements. And then once you've gone through all that trouble, eventually we got some nice soluble, readily processed materials and very nice looking polymers. So we managed to get PIM polyimides, so a polyimide version of PIMs. And all of these really, to me, initially at least, were quite disappointing. These are the hollow circle data in the Robeson plot here, and these are superimposed on the data for PIM1, and you can see that they all form a big sort of data cloud. There's no real big breakthrough in that in any of these polymers that we made at that time. Also, others were playing around with PIM1 and modifying the nitrile group, so making amides, for example, and imidooxines and various other simple modifications of the nitrile. And I'll come back to one of those in particular later on, because I think it is quite an important modification to the nitrile group. So in a way, that was also a little bit disappointing. So again, went really back to basics and remembering what Benny Freeman had told us about chain stiffness. What was the way of making polymers, PIMs, more rigid? And really, the sort of most flexible part of the polymer is the spiro unit. So this spiro center here, you can actually do the molecular modeling, and you can see that it's an extremely flexible unit in your polymer. And But if you fuse a benzene ring to that spirocenter, you get a much more rigid polymer. So this is sort of the energy cost of moving that around that dihedral angle in the polymer. So you can actually sort of see that this is a more rigid polymer just from molecular dynamics. So we made this particular spirobifluorine polymer. And you can do this sort of calculations for all sorts of different structural building units. And what we found was that, that most things are actually more rigid than our original spirobisindan spirocenter. So spirobifluorine I've just shown you, but particularly got interested in making bridged bicyclic units because they're actually very rigid. So things like tryptosine, which I'll show you in just a little while, ethanoanthracene, and also Tröger's base, which I'll come back to in a moment. So let me just show you our initial breakthrough. This is the SPF spirobifluorine PIM, and this was the first one that really gave us anything that was significantly above the 2008 Robeson upper bound for many gas pairs, including oxygen, nitrogen. Just shows a modification of that, which was just sticking a few methyl groups on. This is, once again, comes back to the Benny Freeman idea of pushing the chains apart. You get higher, and when you do that, you get higher permeability. And it's actually predicted before we made it by our collaborators at Correa-Kalina's group. They looked at this and just stuck a couple of methyl groups on. When they did the chain packing models, they predicted that the polymer would have 7% more fractional free volume than PIM SPF1. So that was confirmed by making this a few years later. Now, I just want to show you a bit of a mad polymer. This is taking things to an extreme. And this is never going to be a commercial polymer because it takes 9-step synthesis from commercial starting materials. It's a heroic synthesis done by Grazia Betsu, who's a postdoc in my group. But this is fusing effectively a tryptosine unit onto this spirobisindan. And as you can probably guess from the molecular model, it's swirling around in rather too fast. This is going to pack very, very badly in the solid state, and it does. It gives a very high BET surface area from nitrogen adsorption, still very soluble. We have to really optimize the polymerization in order to get very high molecular mass in order to get film formation. Even then, it was quite brittle. I think it's just because of its structure. It's not really doing chain entanglement in the same way that you'd want. So it's a very brittle material, but nonetheless, eventually we've got a film that was good enough to measure gas permeability from. And this was one of the first ultra permeable PIMs. So we could get from methanol treated film, we got permeability over 6,000 baro with fairly respectable oxygen nitrogen permeability selectivity, which actually rose up to around 5 after 2 years or so of aging. So that was a nice illustration of the Benny Freeman approach, both having a very rigid substituent, but also one that pushes the chains apart from each other to give you higher permeability. Let me just take you back to this diagram. So Tröger's base is a very interesting bridged bicyclic unit because we can use it either as the structural unit itself or actually as the linking unit, because the chemistry for making Tröger's base is so efficient. So let me just tell you about Tröger's base. This is ancient chemistry, chemistry from well over 100 years ago. Julius Tröger from 1887. He actually got the structure wrong when he published it, almost failed his PhD, did Julius Tröger. But the structure of Tröger's base was properly elucidated in the 1930s by Spielmann. But basically, you take an aniline and stew it up with formaldehyde or dimethyl dimethoxymethane in an acid, and you can get very efficient formation of this bridged bicyclic unit called Tröger's base. And this has been optimized in this nice paper in 2008, and you can get isolated yields of 96% or so. What we liked about the Tröger's base was that it's effectively a sort of a non-linear unit itself. So it would introduce what we call sites of contortion in the polymer and break up the linearity of the polymer. So let me just show you the polymer you can make from this. So this is taking a bridged bicyclic monomer from ethanoanthracene, the diamino ethanoanthracene, and just shooting up in dimethoxymethane with trifluoroacetic acid, and we're making this Tröger's based polymer. This is very nice chemistry. All you have to do is mix these three components together, wait till your stirrer stops stirring and it's nice and viscous, then pour it into water, and you can immediately see this. It's got a thread-like polymer, and you can dissolve this material up in chloroform, make very nice films from it. This is a really rigid polymer. All you have here is benzene rings linked together by either Tröger's base bridged bicyclic units or ethanoanthracene bridged bicyclic units. It's extremely rigid, and yet it's a very, very soluble polymer in chloroform at room temperature. So just to show you where the data for these Tröger's based polymers come well above the 2008 upper bound. The best one really is this one made using tryptosine, in other words, doing the same trick as before, fusing a benzene ring onto the site of contortion. And at the same time, there's a very good group in KAUST led by Ingo Pinau, and they were also working on the same principle of making PIMs using bridged bicyclic units, in particular tryptosine. And they made what they call tryptosine PIM1, and we just beat them by about 2 weeks in the same journal, Advanced Materials, for these two polymers. And I've plotted their data onto the oxygen nitrogen Robeson plot as well. Now Ingo is quite impatient. He didn't wait for Robeson to update his upper bound. He actually did propose a new upper bound himself based upon his tryptosine PIM1 and our Tröger's based tryptosine polymer here. And so, i.e. tryptosine PIM1 here and PIM TB here. And this is quite an advance on the selectivity, even compared to the 2008 Robeson upper bound. It's effectively doubled the selectivity of the original 1991 upper bound by using these bridged bicyclic units in PIMs. Now that's not the end of the story, because the data that Ingo used to draw his 2015 upper bound was a fairly fresh PIM tryptosine TB film. It's only aged for about 100 days, and we've now got 5 years later. We've got the data for this film, and you can see that it's now got a really high oxygen selectivity of oxygen nitrogen selectivity of 8, and yet still maintains permeability of over 500 bara. So that's so the 2015 upper bound is definitely not the end of the story. There is still increases to be had in selectivity. So just to summarize that part of the talk, the increase in the in selectivity from P2SP and from 1990s to PIM1 and spirobifluorine, and then the latest result from our tryptosine-based Tröger's base polymers, all composed of bridged bicyclic units. What irritated me for quite a while is that we couldn't really push the the permeability of our PIMs up to the same level as PTMSP. So I naively thought that perhaps if I made a two-dimensional PIM, then perhaps the polymer chains would stack on each other and you get a sort of lamellar liquid crystalline type of packing, and you get the sort of free volume in here would be sort of aligned with each other, and you get massive increases in permeability. That was the idea. So we made these two-dimensional PIMs from these benzotryptosine type building units, and we got Corey Kalina to do her modelling of the chain packing, and in fact there was no two-dimensional stacking of the chains. And if you look at it, it's just amorphous packing for both this SBI based polymer and these two-dimensional. So the two-dimensional and three-dimensional chains seem to pack pretty much the same. However, there was a lot more fractional free volume as a result of the two-dimensional chain, so something like 25%. So this blue area in this model is a bit more than the blue area in this fractional free volume for the three-dimensional polymer. So it appears that two-dimensional chains pack three-dimensional space less efficiently than three-dimensionally contorted polymers, which was a bit of a surprise again. Let me just show you the data for that. This is the first two-dimensional polymer that we made, and once again we're getting very high permeabilities up to around 10,000 bara now for methanol treated films. Quite respectable selectivity, as you might expect, because this is based on a bridged bicyclic rigid monomer, and it ages very gracefully over about a year up into the 2015 Ingo Pinau upper bound. Now we made a whole series of these benzotryptosine based PIMs, and in fact the one without any substituents on at all we found was initially insoluble, and we realized that quinoline is a sort of magic solvent for many PIMs that appear insoluble, and we could cast the film out of quinoline quite nicely, and we're getting very, very high selectivities for when you have no substituents on the benzotryptosine. You get very high selectivities, once again above the 2015 upper bound. So this is aged over a year. Once again, we're approaching above 7 for selectivities for oxygen and nitrogen, but we're still with oxygen permeability of around 1,000 bara. Now, we've done, in collaboration with ITM, who are our collaborators who do our gas permeability measurements, and they have a very nice bit of kit that allows you to do gas permeability measurements on the time lag equipment, so you can get permeability and diffusivity out from this measurement, and you can also do these measurements at different temperatures, ranging from say 25 up to around 55 degrees centigrade. And so you can actually do sort of Arrhenius type analysis of the mechanism of gas transport. But what you can see, just eyeballing the data here, is that for small molecules such as hydrogen and helium, there's very little dependence on the temperature. So you get very high diffusivity, but it doesn't really change very much if you increase the temperature. Whereas for larger molecules such as nitrogen and methane, it's very much temperature dependence, and you can get very, very much greater diffusivity at high temperatures. What's actually quite interesting from this is if you cool the membrane down, say to 0 degrees centigrade or something, you can really increase your selectivity. And I think Ingo Pinau just brought out a very nice study on doing this for tryptosine TB polymer, and so you can really get very nice selectivities at lower temperatures. But back to the mechanism of from this data. You can see this is the activation energy of diffusion for all of these various gases, so helium, hydrogen, up to methane. And you can see for PTMSP, there's almost no difference in, it's a very flat correlation between diffusivity's activation energy and the diameter of the molecule. Whereas for our highly selective PIM benzotryptosine, you get a very large, again, a much steeper slope. So it's much harder to effectively. So let me just show you for hydrogen. In effect, the micropores and the free volume are effectively interconnected for small molecules. If you're a small molecule trying to move through this PIM, you're not really seeing any barrier to transport. You can move through this contorted network of free volume quite readily, and there's nothing really stopping your transport. Whereas for larger molecules such as nitrogen, you're really trapped in these elements of free volume, and to get from one element of free volume to the next, you have to wait for a thermal motion of the polymer to open, and so you can hop from one bit of free volume to the next. And because these polymers are so rigid, that's very unlikely to happen, and therefore you've got a much higher activation energy for the transport of larger molecules. And that's where we're getting these very high selectivities from these bridged bicyclic polymers. So just going to show you a little bit of data for CO2 methane of the Robeson plot. And in effect, most of even our bridge bicyclic and Tröger's based polymers didn't really show spectacular results compared to the 2008 upper bound, and plotted to them with some of the best performing ones here, but a sort of marginal increase for the best performing for this important separation, which is useful for natural gas upgrading and biogas upgrading. But our new benzotryptosine based PIMs really showed a very nice increase in selectivity for this gas pair, particularly the polymer I've just been talking about, the unsubstituted benzotryptosine. And so we've now done what Inge and Pinot did, and we proposed our own update to the CO2 methane Robeson plot, because in fact Ingo did not propose an update for CO2 methane or CO2 nitrogen, and this just came out last year or so. But the trouble, the Robeson plot is, as a real membrane scientist would tell you, somebody like Ingo Penau would tell me many times, is that the Robeson plot for CO2 methane is fairly irrelevant. And that's because you do this separation at such high pressures that you get plasticization, swelling of the polymer, so your selectivity drops because of this plasticization. So just to show you the data for PIM1, this is from Ingo Penau's paper last year. You start off with a fairly respectable, at 1 bar pressure, you start off with a fairly respectable selectivity of around 15 or so. But then if you increase up to 50 bar, something like that, something reasonable for natural gas separation, then it drops down to a selectivity of 5, which is pretty useless for a real life application. What Ingo found is that if you modify the nitriles by this amidoxine modification to give you this hydrogen bonding type of functionality on your PIM, you can actually retain a lot more of the selectivity. So this is the amidoxine modified PIM1, starts off at quite a nice high selectivity, and even at 50 bar, you're getting a workable selectivity of around 15 or so, which is pretty similar to cellulose acetate, one of the main polymers used in industry at the moment. So we thought about how do we increase the performance of PIMs for CO2 methane processing, and we thought we'd do it not by just diffusivity selectivity, but also try to increase the solubility selectivity of our polymers. And the sort of inspiration from this would be from Zach's lovely analysis on fluoropolymers, where he shows that because of the weird sort of differences that you get in fluoropolymers, you can actually see some very high solubility selectivities for certain gas pairs. Now, in actual fact, CO2 methane was not one that he analysed, but classically helium methane shows you can get a very much greater selectivity for using perfluorinated polymers than you can for hydrocarbon-based polymers. So we went to some trouble of trying to make a two-dimensional bridge bicyclic PIM, which had fluoroalkyl substituents in the polymers. And we also felt it important that we could have a comparison, a direct comparison with a normal hydrocarbon type substituent. So we devised these two monomers as a pair to analyze just by some nice Diels-Alder chemistry. These are actually monomers that have been used for ROMP chemistry, so quite easy to make, and they add on to this anthracene quite nicely. We get polymers out quite nicely. Corey Kalina did the modeling, and this was quite nice because it showed that the fluorinated and the non-fluorinated polymers pack pretty much identically as far as her calculations are concerned. So the fractional free volume is pretty much the same in both of the packing models for both of these two polymers, this pair of polymers. So just to show you for the classic fluoropolymer gas mixture, which is helium methane, these are the quite impressive increases, which we believe is due to the solubility enhancement because of the fluorinated unit on the PIM. So we get well above the 2008 upper bound for helium methane for both this polymer and the amidoxine modified polymer as compared to the hydrocarbon analog. So this looks like a proper solubility enhancement of the selectivity. But we also seem to get a similar solubility enhancement for CO2 methane, taking us just above our newly proposed 2019 upper bound for CO2 methane. So this is comparing this fluorinated with this hydrocarbon type polymer, and you can see that you get a significant increase in the selectivity. Both of them are highly permeable, as you might expect for a two-dimensional polymer, but there does seem to be this slight enhancement of which we think is perhaps due to fluorocarbon effectively not liking methane. So fluorocarbons and hydrocarbons don't like each other very much, and therefore it's not so much that this polymer likes CO2 so much as that it doesn't like methane, and that's possibly the reason why we're seeing an increase in selectivity. We also see something similar for the amidoxine modified polymers. So we're actually getting quite nicely above the 2019 upper bound for this amidoxine modified material, and we want those amidoxine modifications in there to give the hydrogen bonding to maybe give a bit more resistance towards plasticization. But we're getting a sort of CO2 methane selectivities of 40 for many thousand bara of permeability. In actual fact, you can, for mixed gas separations, at 1 bar pressure, then we're actually seeing an increase of selectivity almost up to about 50 for CO2 methane. Although as we increase up to about 6 bar pressure, which isn't enough for natural gas separation, but it's probably okay for biogas separation, then we get down to the 2019 upper bound. So these are pretty respectable figures for CO2 methane separations. And same is true for the amidoxine. That's in there again, sorry. So we actually sent these polymers to Carol Fries, who does solubility measurements for us directly on the polymers, and he does seem to indicate that there is a little bit of solubility selectivity from these from the fluorinated polymers relative to the alkyl polymers. Although I have to say, after chatting to Zach yesterday, it could well come from the added polarization of having this electron withdrawing group on this this substituent and this alkyl group actually polarizing the substituent on the molecule, and that might be what's interacting with CO2, for example. So it's not it's something that we still can discuss. So I just want to finish off with pointing out a few other applications. I'm going to talk a little while about membranes for batteries and electrochemistry, but there are now some commercial applications. In particular, there's this sensor or an end-of-life indicator on this this respirator cartridge that 3M use. This is a very thin film of PIM1. And it's so thin that it refracts light, so it looks green. And then as it absorbs organic vapor, it changes refractive index and changes to a red color. And when this bar goes from one side to the other, you know that the activated carbon in the canister is all used up, and you throw away your respirator and get a new one, so you're not taking in the organic vapor. So that's a nice application that has been developed by 3M. There's uses for pre-concentrators for organic vapor sensors, the Seacoast Science as well, but there are all sorts of different membrane applications. There's a strange one that came out last year, which I don't really understand, which is PIM1 helps robots play piano. I'm not even reading this paper many times, I still don't quite understand what's going on. You take PIM1, you heat it up with anhydrous zinc chloride, you make something that looks a bit like a coronavirus, and then things go in and out of what looks like the coronavirus, and then you get robots playing piano. I'm not quite sure what's going on, but perhaps somebody can enlighten me one day. but it's quite nice to see all these various different applications of PIM1, which I never would have thought of when we developed it all those years ago. So we have a very nice collaboration with Frank Markham. I send him a few grams of PIMs, and he sends me about every week a manuscript of a paper that he's written, which is a very nice type of collaboration that we have. He's a very imaginative electrochemist, and he's done all sorts of things with coating electrodes and making sensors and all sorts of things from PIM1 and ethanoanthracene Tröger's base. I think one of the most interesting things he's done is make ionic diodes, which he uses as sensors, but also he's devised this method of using AC current as a desalination thing based upon an ionic diode, which is analogous to an electric diode, where you can get sort of positively charged ions moving, but it blocks negatively charged ions moving in the opposite direction. So it's kind of an interesting application. We've also collaborated with Haifa University in China, and they've been looking at our quaternarized Tröger's-based polymers as ion exchange fuel cells, and they've got some very high hydroxide conductivities at high temperatures. Unfortunately, they're not stable enough for a long term, so we need to play around with some of the structures to make these more stable, but it's some very interesting initial results there. About 4 groups independently came up with the same idea basically last year of using either PIM1 or a Tröger-based PIM to coat the electrodes in the lithium in lithium batteries to stop dendrite formation, but allow the transport of lithium ions back and forward through the separator. And this seems to work very well for lithium batteries. So that's quite a nice application. But all sorts of battery applications now are emerging to a degree. A lot of this has been done, but by Brett Helms at the Molecular Foundry over in Berkeley. And Brett has this nice quote that basically PIMs manifest as a universal platform to address crossover problems in batteries and to significantly advance the field of electrochemical energy storage. It's quite nice. We're actually entering this field in collaboration with Chili Song at Imperial. And what we're interested in is making PIM membranes for aqueous redox flow batteries. If you don't know, this is what a redox flow battery looks like. Imagine something the size of a swimming pool or something. It's going to be a massive battery for storing excess energy from renewables, so you can use it when the wind drops and the sun doesn't shine, etc. So what you have is redox active molecules on both sides, separated by a membrane which is permeable to ions, say potassium ions, but blocks crossover of the larger redox active molecules, such as anthraquinones and these prussic acid type anions. So it's effectively the same problem. You want rapid transport of small things through the membrane, but block out the bigger molecules. So a very simple experiment you can carry out is use these H cells, and you can see that for this amidoxine modified PIM1, you can get a very rapid transport of potassium through the membrane, but you block this anthraquinone based redox molecule. And what this allows you to do is to build very stable quite high performing redox flow batteries that have greater stability over a longer time and number of cycles than the equivalent battery that's been made out of Nafion, which is the sort of currently used sort of state of the art for making redox flow batteries. So this is kind of a nice application for PIMs, and we've just developed a nice new method of sulfonating PIMs. So we've got some even more highly permeable membranes for potassium, but which block larger molecules very efficiently in redox flow batteries. We've been able to make very efficient redox flow batteries very recently. So that's the end of the talk. Really, I just want to conclude with a couple of statements. Really, the concept of PIMs is one where you can control, in a solution processable polymer, the free volume that you get from your polymer. And that's quite a powerful concept. We found that extreme chain rigidity really provides very enhanced molecular sieving for separations, particularly for gas separations, but now other separations are emerging as well, such as nanofiltration membranes, and also, as I've just shown, in battery separators for redox flow batteries. We can now get, after quite a lot of trying, it has to be said, PIMs can now provide the highest gas permeabilities for all polymers. We're just beating now PTMSP for methanol treated membranes at least. And as I just showed you, applications are rapidly emerging in batteries. If you want to check out a recent review, it shows you this sort of concept of PIMs and why PIMs are, I believe, are very form a very distinct class of polymers, then I just wrote this review in Polymer, and it's been out to celebrate the Staudinger's 100 years of the macromolecule concept. But I should update this. There's been over 750 publications on PIMs now. I'm keeping a kind of a count of these on my website. I haven't been very busy, so I haven't got around to looking at 2020, but I believe there's something like 140, 150 publications on PIMs in 2020, and something like over 180 patents. So just to give a few acknowledgements, my key collaborators have been Peter Budd on the certainly initial days of he suggested the membrane applications. He's been a great collaborator over these 20 years. We're still collaborating on a few projects. John Jansen did all the gas permeability measurements, and so doing some very sophisticated experiments with those polymers now. Detlef Fritsch is now retired, but he did the original gas permeability measurements back in 2005. Frank, who's doing all those electrochemical measurements. Corre, whose group does the packing, the modelling of the packing of PIMs for us, and Chile, who does our work on our redox flow batteries. And lastly, my group, just to point out a few key figures. Kadam Musayab was the first person to make PIM1, that was 20 years ago, and was the first person to make it, analyze it, see it was soluble, and put it on a on a nitrogen adsorption rig. So a very important person in the development of PIMs. Rich and Lino devised between them the Tröger-based chemistry for making bridge bicyclic compounds. Grazia did that fantastic spirobifluorine work that I showed you, and Ian did the two-dimensional. Or Ian and Bibiana did the two-dimensional polymer work, and G also did that lovely fluorinated, non-fluorinated work to look for solubility enhancement. And with that, I'll thank you for your attention, and I'm very happy to answer any questions. Thank you.
All right, well, thank you, Neil, very much for the very nice talk. We'll take just a few questions here. If there are any from the audience, you can either raise your hand, enter in the chat box, and I will call on you. Well, Neil, I might have to get us started with a quick question. Let me ask this one really quick, and I'll call on Francesco here. I was curious about the aging data that you have. When you're looking at the upper bound, that slope hasn't changed over the years, but as these polymers age, the trend over time does not follow the upper bound. So maybe you could speak a little bit more on what exactly you think is happening during that aging process that's changing the slope of the upper bound.
Well, I guess there's no real reason why in our polymers it tends to why it should follow the Robeson upper bound. In effect, what's happening, I think, is if you plot it, it goes like this. So initially it's quite flat. I mean, aging is a strange business. In effect, when you place a PIM into methanol, you're really getting a lot of excess free volume, and that free volume can be lost very rapidly. In fact, you can get ridiculously high permeabilities when you measure the hours after methanol treatment. So we tend to leave it in a vacuum for a day or so to take the first measurement. It's kind of stabilized to some degree, but it's really losing a lot of that, and you can imagine that initial free volume is highly interconnected, and that's going to really reduce the selectivity of your polymer quite greatly. And then as you lose that excess free volume, then you're starting to see this sort of increase in the selectivity. There's no real reason why it has to follow the Robeson upper bound, I don't think. we generally see that it kind of goes like this, and it sort of gets steeper as it ages.
Yeah, very good. Thank you. Francesco, I don't know if you still have a question.
Yeah, so thank you so much for the talk. It's always nice to go through the whole history of PIMs. It's just a beautiful story. I had one question about like related to the observation that you made that competition can enhance CO2 based separations like CO2 methane, CO2 nitrogen, right? And I've seen that you also brought the argument that the polymer that showed that type of behavior had a higher solubility selectivity, right? So there's some sort of solubility selectivity contribution to that competition that you see. And the two questions that I have are, so the first one, what is the polymer in your experience among all these PIMs that you investigated that showed the most enhanced comparative sorption enhancement of selectivity? And this would be the first question. And the second question, as you showed like solubility selectivity for pure gas, if you ever thought about running some mixed gas sorption tests to see how actually at fundamental level that solubility enhancement can help.
So the latter one is would not be stuff that I would do. I think possibly Carol Fries in Prague might be able to do mixed gas solubility experiments, but I know you guys that I probably do these sort of things, and perhaps the Bologna group perhaps also can do these mixed gas. I mean, I follow their work with great interest with it on, and clearly solubility is a complicated business particularly in a PIM, a high free volume polymer. But no, we haven't done any mixed gas solubility studies. We do, I say ITM we're doing, and now moving on to mixed gas permeability studies, but not solubility studies. I didn't quite understand your first question.
So the first question was around, so you've seen some enhancement in permeability selectivity due to the competition effects. And I was wondering if that is common, like of all PIMs show more or less a similar type of enhancement, or there are some PIMs that show more than others?
Yes, I mean, this may
in your experience.
This idea effectively of pore blocking, and this is something that Ingo is actually quite interested in, I think. So, for example, if you have if you're trying to separate, say, butane from hydrogen, you might anticipate in a PIM being highly size selective, the hydrogen would be much more permeable and much more selective for the hydrogen. But of course, if you've got a larger, highly soluble thing like, say, butane, that will be soaked up by the polymer and effectively block the pores for the transport of hydrogen. And that's actually been demonstrated quite nicely for a couple of mixed gas experiments. But so that's something I think that could actually be quite industrially useful. I suspect that there are some industries out there looking at this, because I think the solubility could be this pore blocking effect could be quite extreme when you're dealing with a highly adsorbed molecule, such as, say, butane, for example, or some other hydrocarbons.
Thanks.
Very good. Well, maybe if there's one more quick question. I think it's almost 10 p.m. your time, Neil. So this is a late talk for you.
I've gone on too long. Sorry about this.
Any final questions from the audience here? Well, I think for now, let's give another round of applause. Neil, I'll stay on for a few minutes here at the end as well. But thank you so much for the presentation and for giving that overview on this really exciting field. We really appreciate your time and for you virtually visiting us. We look forward to having you in person at some time in the future. But thank you so much again, and take care, everyone. All right, and Neil, I wanted to follow up on the fluoropolymer question.
Oh, you might.
Yeah,
yeah.
Yeah, I was really curious about those results, and I was wondering about the role of sorption as a function of critical temperature or Leonard-Jones parameters. Have you looked at that sorption effect, maybe with your collaborators, and how sorption changes as a function of the critical temperature or some other metric of the gases you've been looking at? I'm kind of curious if the slope changes in that type of analysis when you add fluorine into the PIM.
No, I mean, simple answer is no. We haven't. I mean, we've all we have is some CO2 methane adsorption, as I showed you. I have to say that these polymers, I've sort of cherry picked the data a little bit as well. They're quite difficult to handle. I mean, they're very nice. You make very nice films, very nice robust films, but you get the feeling that there's often stuff that's still stuck inside. So we get quite a particularly, I mean, for the AO ones, which I think that they seem to be much more amenable to giving us the same result each time. But the aging effects of the fluorinated polymer in particular are quite strange. Sometimes they just don't seem to want to age. Sometimes they age quickly. Sometimes they age as you're making the measurements. It's like there's a sort of semi-stable state it gets into, and then all of a sudden it sort of decides to age like a normal PIM. It's been quite difficult to get a grip on. We've remade it many times now, and we've got a whole battery of data. But I'm not. But it's like until I see sort of like 3 or 4 very consistent data, I don't really want to publish it. But the data, I mean, the data tells us pretty much the same story. It's just that they're often, all over the place with permeability. But relative to their selectivity, they're fine. But I say it's quite a tricky polymer, and I think that's probably down to the fluorocarbons and having a low cohesive energy between the polymer chains.
Yeah, it's fascinating. It would be really neat to look at some of the absorption isotherms and to break them apart into dual mode parameters, look at melt modeling. There's a lot of really neat things you could do there to try and uncover what that difference is in the packing rate. But I think there might be a few people who are on here waiting to say hi. I don't want to hijack the whole conversation. But yeah, just really, really interesting work. And I think the fluorinated aspect is a really neat.
The fluorinated stuff is something we've got a bit of a bug for now. And so, I mean, that wasn't a particularly difficult polymer to make, but it's not one that's like PIM1 or something. And so we're looking into easier methods of getting fluorines onto PIMs, and perhaps when we do that, we'll be able to send you some.
Yeah, no, definitely. I would love to run some of those tests too. Those are really, really neat materials. It's nice to see that combination of the solubility effects that you're adding in now to the diffusion.
Yeah, work. I mean, for the gases for the gas pairs in your paper, you can definitely see the effect. So, but we also see, but I actually I kind of take your point about the CO2 methane. And it may well be that you've just got a more polarized structure to your PIM, which may just have might just latch on to CO2 that little bit more.
Yeah.
So it may not be a fluorocarbon effect so much as the electron negativity of the fluorine working its way through the carbon system, basically.
Yeah, there's sort of this question of almost spreading pressure or surface coverage. If you do it as a microporous material, what's the solubility at the lowest pressure versus at a higher pressure, where you may start to screen some of those fluoro effects? But it's just a really fascinating material to work with. I think there's going to be a lot that comes out of that. There are a few people on here, and I've been talking a bit, but maybe I'll stop if anyone has questions wants to jump into, if that's okay with you, Neil. I know it's
it's fine by me. Yeah.
Or they might be listening in.
No, doesn't sound like
Maybe
it.
not. Yeah. So yeah, mystery people who are still here. Well, I think, with that, I may jump off here now. I've got to call into another Zoom call actually, but thank you again for.
It never stops. It never stops.
I
hope I didn't go on too long. I wasn't. It was perhaps one of the dangers of doing a talk at sort of 9 o'clock at night.
Yeah, exactly. But it's one of those things that you miss out on a lot of the fun for an in-person visit. And so it's nice to see you on Zoom, but I really do wish we could do this in person. Hopefully in the future,
I'm sure we shall. I'm sure we shall. And I say when we have some sensible quantities of a fluorinated polymer, it's got your name on it.
Fantastic. Yeah. But thank you again for accepting the invitation. I really enjoyed the talk and seeing the whole field develop there over the course of just a few slides. So thank you for putting that together. And for the overview, I can't wait to see you in person in the future. Sometime, hopefully soon.
Cheers, Zach.
All right. Take care, Neil. Thank you again.
Cheers. Bye.